Now that we've looked at congruent triangles, we're going to look at similar triangles. So remember, congruent meant same shape, same size. Everything was the exact same. Similar means it's the same shape, but a different size. So remember back when we did transformations, we talked about dilations. That transformation proved or created similar figures because it was the same exact shape, but it was either bigger or smaller in our coordinate plane. Right, so we're going to look at different ways of proving triangles to be similar instead of congruent now. Now remember we talked about, we had sides and angles and all those different versions for congruency, and we talked about how angle, angle, angle didn't prove them to be the same size, but it did prove them to be the same shape. So that's our first similarity postulate. All right, and we actually only have to call it AA, angle-angle similarity, because if I know two angles in a triangle, I know the third one, because they all have to add up to 180. So once you know two, you know all three. So we call it the angle-angle similarity. And that's when two triangles are similar if two angles of one triangle are congruent to two angles of another. All right, and this actually should have two curves on that one. So we have one curve congruent, two curves congruent, which automatically makes the third angle congruent. So then these must be the same shape. They must be similar. All right, now remember with congruence triangles, we wrote an equal sign with a squiggle above it. Okay, that was congruent. Similarity, we take out the equal sign. All right, so similar triangles, we would say a squiggle. Alright, so then we have side, side, side similarity. So there's side, side, sides for congruent triangles and for similar triangles. And it doesn't mean that all the sides are the same, because if all the sides are the same, the triangles are the same. Similarity talks about there being a proportion between the two sides. Alright, so it says if two triangles are similar if the lengths of their corresponding sides are proportional. So for example, if we look at this triangle, we have 8, 10, 14. So if we go in order over here, we have 4, 5, and 7. So if I take 8 and divide it by 2, I get my 4 over here. Then if I take 10 and divide it by 2, I get 5 over here. And I can take 14 divided by 2 and get 7 over here. So if I take all the triangles of the first, or all the sides of the first triangle, and divide it by 2, I get the second. So that means that the sides are proportional, so these triangles are congruent. And our third one is side, angle, side. Just like before with our congruence statements, this angle is in the middle, so we call this an included angle. And it's got to be the angle that touches both of the sides that we're working with. Right? So this one says that two triangles are similar if the measures of their two sides are proportional and the included angles are congruent. So for this one, I've got a red curve and a red curve, so those are my congruent angles. Then if I look at the sides, I've got 9 and 12, 3 and 4. If I divide by 3, I get the side 3 over here. And then if I divide by 3, I get the side 4 over here. So my sides are proportional, and I have the included angles congruent. So now we're going to use all of this to solve problems. All right, so in this case, I'm given that RS is parallel to UT, and we've got the arrows labeling it. I know RS is 4, RQ is x plus 3, QT is 2x plus 10, and UT is 10. I want to find the length of RQ and QT. Well, just by looking at this setup, I see vertical angles in the middle. Parallel lines tell me that I have alternate interior angles, and I have two sets of those. So I know that these triangles are congruent just by the AA similarity theorem. Okay, so now that I know that they are similar, I know that all my sides have to be proportional. So I'm going to write a proportion. So I'm going to take the one side over here over top of the corresponding side in my second triangle and set it equal to my one side over top of the corresponding side. So in this case, we have 4 over 10 equals, and then the same relationship would be x plus 3 over 2x plus 10. Anytime you want to solve a proportion, we can cross multiply. So we have 4 times 2x plus 10 equals 10 times x plus 3. Distribute, and we get 8x plus 40. Distribute, and we get 10x plus 30. Now I want to get x on the same side, so I'm going to subtract the 8x over. So 40 equals 2x plus 30. Subtract the 30 over, we get 10 equals 2x. Divide by 2, x equals 5. Now remember, this wanted me to find RQ and QT, so I got to plug x back in. Well, RQ equals x plus 3, so 5 plus 3 equals 8. And QT is 2 times 5 plus 10, so that's 10 plus 10, which is 20. For example 2, we want to find x. And so if I take a second to look at this drawing, I've got this smaller triangle, the red one, that is somehow relating to the large triangle, which I'll outline in blue. Right? So if I look at these, I've got an angle that they both have. They both have this angle up top, reflexive property. And then I've got these parallel lines, which are labeled with the arrows. So that tells me that I have corresponding angles in those corners. And now I know that these triangles are similar because of the AA postulate. Okay, so now I'm going to write up the same type of proportion as we just did. But this time, keep in mind that this 6 is not the entire side length for the big triangle. It's only part of it. Right? So if I start with that 4, it corresponds, this side here corresponds with this whole side of the big triangle, which would be 6 plus 4, which is 10. And then this 8 corresponds to the bottom of the big triangle, which is x. So we have 4 over 10 equals 8 over x. My proportion, I can cross multiply, so I get 4x equals 8 times 10, which is 80. Divide by 4, and we get x equals 20. And for our last example, we got a word problem. So Josh wanted to measure the height of the Sears Tower in Chicago. He used a 12-foot light pole and measured his shadow at 1 p.m. The length of the shadow was 2 feet. Then he measured the length of the Sears Tower shadow, and it was 242 feet at that time. And we want to know the height of the Sears Tower. So we got this lovely drawing down here for us. And so if I look at my triangles, I've got this smaller one down here, and then I've got the big one. Right? They both share this angle, and again, because of these being vertical lines, they're parallel, so I've got angle similarity. Right? So I'm going to do the same thing, write my proportion. So that 2 on the bottom corresponds to the 242-foot shadow. I'm going to set that equal to the height of the first measure, which was 12, over the height of the Sears Tower, which is x. And then we cross multiply. So we get 2x equals 2,904. Right, 12 times 2, 42. Then we divide by 2, and so we get that the height is 1,452 feet, approximately. Right, this is all just estimating. But we're going to use these similarity theorems and then these similar triangles to be able to prove or see how tall other figures are, because they have to have that same proportion with all of the sides.